Okay, I'm going to do a quick review of basic concepts and equations. Maybe spend, I don't know, 3 to 5 minutes. You can skip that if you like, but I recommend you listen. And then we're going to dive into the physics and the specifics around the later problems in Assignment 9 and the last 5 parts of the last 5 exercises in the lab, because as you know, the lab video, the sound of the lab video cuts out at about 10 minutes, so about 2/3 of that video is lost. And I will, in the later part of this video, cover those last 5 exercises of Lab 9. So, the review part. All magnets are dipoles. Our basic idea of a magnet is a bar magnet with a north and south pole. And we now know that magnetic field lines don't leave the north pole and enter the south pole. They go right through the magnet. So all magnetic field lines are closed loops. And a dipole magnet is similar to an electric dipole, only that in the case of a magnet, the field lines don't end, and so if we cut a magnet in half, we end up getting 2 magnets, and if we keep cutting it, we keep getting magnets. And so the basic way to think about a magnet is a coil of wire where the current goes around and the magnetic field goes in and out of the coil, right through the coil, and forms a dipole field. And all of this arises from the observation or the knowledge that an electric charge that's static in a magnetic field is not affected by the magnetic field. It's only if the charge is moving, because a moving charge has its own magnetic field. So a wire carrying current has a magnetic field, which is circular loops around the wire. And if we bend a wire into a coil, then that magnetic field ends up bending in a way such that it's still circular field lines, but as it passes through the coil, it's a uniform field. So if that is not all clear to you, then you should go back and rewatch that first video. Actually, I recommend you watch it a couple times, one early and then later after you've done a lot of the problems. So the equations that relate to what I just talked about are these 4 equations. If you look at your equation sheet, these are spread out, they're not all clustered. But for now, these are our working equations, and you should recognize these as the way to calculate the force on a moving charge in a magnetic field, and the notation V cross B is written out as VB sine theta. And so this is the force on a charge traveling through a magnetic field. If you have a wire in a magnetic field, it will have a force on it according to this equation, I L cross B, where L is the length of wire in the field, and B is the magnetic field, and so it's ILB sine theta when we write out the cross product. That's a Calc 3 notation, but you should be familiar with it by now because you used it in torque. And then for our current carrying wire, which has a circular magnetic field around it, this is the equation we use. On your equation sheet, it does say B wire. So the field, remember, this is a field, so we have a wire and we have a point. We pick some point and we want to calculate the field. We will take mu naught, that's the magnetic equivalent of epsilon naught. We take the current in the wire, obviously more current, more field, and we divide it by 2 pi a, where a is the distance from the point we select to the wire. So if I pick a point here, a would be that distance. And so the closer to the wire, the stronger the field. Makes sense. Now if we bend the wire into a loop or a coil, then the field inside the coil, and on your equation sheet this reads B coil is mu naught N over L times I. Once again, the field inside the coil, right? There's a coil. The field inside the coil will depend on the current in the coil, no surprise, and the number of windings per unit length, so the winding density, right? If you have a lot of windings and they're spread out, it will be a weaker field than if you have a lot of windings in a small amount of length. So mu naught is the constant. It depends on the current and the winding density of the coil. And what you should know, because it comes up in all these problems, is when you are inside a coil, the field inside that coil is uniform. So outside the coil, the field is going to be circular loops. But as those loops pass through the coil, whoops, oh well, they look like the magnetic field inside a magnet. And so inside a coil is a good place to get a uniform magnetic field. And we'll talk about that because in the assignment and the lab, there are lots of places where we have charges going through uniform magnetic fields. Okay, that ends my 6.5 minutes of review. I hope that all seems clear to you. Now let's talk about the situation that shows up in a lot of the problems at the end of the assignment and in the last 5 exercises in the lab. We have a place where we have a uniform field, and we know that a magnetic field, a vector, any vector, going into the page is an X. And so uniform field means evenly spaced field lines. And so when you see this, you're seeing a uniform magnetic field going into the screen or the page. And if you saw this, dots or circles with dots, you're seeing a uniform magnetic field coming out of the page. And if we take a charge and it goes into the field, so let's take a positive charge going into this field, as long as it's outside the field, there's no force on it because it's QVB. You have to have a field. Once it enters the field, it has a force on it according to F equals QVB sine theta. And so that force, by right-hand rule number 1, my index finger goes in the direction of the V vector. My middle fingers point into the screen in the direction of the field, and my thumb points up. So I know the force on this particle is going to be up. And so as it travels through here, it's going to bend up. But the direction of the force doesn't remain up, right? If the particle ends up moving up, now the force is still perpendicular. So because of the F equals V cross B, because the force is always perpendicular to the V and B vector, that force is always perpendicular to the velocity. So very important, when a vector is perpendicular to the direction of motion, it changes the direction, it bends it, but it doesn't change the speed. So these particles that go through the magnetic field move in circular paths without their speed changing. For that very reason, that's important to grasp. And so that leads to, well, let's try another one. Well, you can almost guess. A particle going into the field in the opposite direction should do what? It should bend down. Let's check. Point your index finger in the direction of I hat. Your middle fingers coming out of the screen in the direction of K hat, and your thumb points down which means the particle will bend down and move in a circular path as it goes through the field. And you always have to remember, be careful not to make a mistake. If a negative particle goes in, it has to move in the opposite direction, because when you get the F, you multiply the V cross B by Q, and so if Q is negative, it changes the direction of the force. And so a negative particle entering this field will bend up and move in a circular path like that. So here's the situation you're going to see in a lot of the lab exercises and in the assignment problems. A charged particle enters a field. We just talked about that. This is an electron. So we did this already. Index finger along the x-axis, middle fingers negative K, thumb points up along the y-axis, but it's a negative charge, so it's going to bend down in a circular path as it enters the field. And so the equation that describes that force is going to be qvb sine theta. But since the velocity vector is along the x-axis and the field is along the z-axis, it's going to be 90 degrees, and so the sine of theta becomes 1. So we can ignore that. And how is it going to move? Well, what we see is that the force, always perpendicular, it moves in uniform circular motion. The velocity doesn't change. So we know about that from first semester. So the force on the particle, ignoring the force of gravity or any other forces, we get the force on the particle is qvb, and its motion is m times its acceleration, and for uniform circular motion, that's v squared over r. So we have a v here. That cancels one of the v's of the v squared. And so we're left with this equation, and this equation coming from this simple analysis is the equation we use in so many problems again and again and again. So if we knew this is an electron, then we would know its charge, we know its mass. If we knew the field strength and we measured the radius of curvature of the path, then we could calculate the velocity. So as long as we know all the quantities in this equation, we can calculate the other. So this equation gets used in many different forms, right? And in the mass spectrometer, we use it to find the mass of the particle. So if we solve it for mass, what do we get? We get that mass, just doing the algebra, equals QBr over V. And so just remember, this is the basic equation that can be transformed into many different forms to solve any problem where you have a charged particle in a uniform magnetic field. So we talk a lot about uniform fields, so you should know there's 3 situations in which we can create this. And since we're not in class and I can't show you real things, I'm going to have to show you pictures of things. But the first way to create a uniform magnetic field is to take 2 magnets and put them opposite poles close together, and the field lines leaving the North Pole will go into the South Pole. This is like 2 charged plates, right? And so even though the field lines here are closed loops, the field lines in here are going to go through the magnet, through that, right through that gap around these, and then there'll be some field lines like that, right? So in between the pole faces, we get a uniform magnetic field. So we can create that kind of field between 2 pole faces. Here's an example of that. I'll come back to this in a minute. The other way is a horseshoe magnet, right? So you see this kind of uniform field in the face of that horseshoe, in between that horseshoe magnet. So the field lines, if this is the North Pole, whoops, and this is the South Pole. And the field lines come out of the North Pole and go into the South Pole. And in this area between the magnet, the field can be fairly uniform. In the other parts, the field lines go through. We get a lot of other kinds of field lines like that. But in this volume between the pole faces, we get a fairly uniform field. So we have some examples of that I'll show you in a minute, like here, a horseshoe magnet and a uniform field in that volume. And the third way is a coil of wire. And a coil of wire has a field that looks like a bar magnet. So the field lines go like that, but inside they're going to be fairly uniform, especially if the coil is long and narrow, right? So you can see inside the coil we have a uniform field, and we talked a minute ago about how to calculate that. So let me show you some devices that actually are real devices that show this. So I already showed you this diagram of the horseshoe magnet. It's not a real one, but it's a diagram. But you can see the field is fairly uniform in between the pole faces. And this is showing you the same thing, where we have, it's big and wide, so it creates a fairly big volume of uniform field. And here's a diagram of a horseshoe magnet that has round pole faces. So you see in this one we have a magnetic field between the pole faces, and then we'll talk about this in a minute. We have perpendicular to that two plates which create an electric and magnetic field which are perpendicular to each other, right? That's the velocity selector problem. And the coil of wire. But it's hard to work inside a coil if it's solid. So what we often do is we take two coils and we have a gap. So you see there's a gap there, and that allows us to put some instrument or probe inside the coil, and we can still see it. And in some cases that gap may not be big enough. So what we do is we take, this is an apparatus that we actually use in lab, but we're not in lab. We have two big coils, you see them, and we can control the current through the coils, and we put our device where we're going to look at the charged particles at the center of these two coils. And that's an area where the field also is fairly uniform, and we can control the field strength by controlling the current in the coils. So these are all real devices, or diagrams of fairly looking real devices. So, okay, we're 18 minutes in. Now let me talk. I'm going to go right now to one by one to the lab problems and talk about them. Okay, here's problem 27. Let's see if it'll run for me on the screen. Good. So this is an electron, if you read the description. Notice it bends down. Then it appears to go straight. Now it's bending up. It's continuing to bend in the same direction. Continuing to bend in the same direction. It re-enters region 2. And then it goes back out. So it's symmetric. It reverses itself. So let's think about it. It's an electron. So it's moving along the x-axis. I want my thumb to point up, right? I mean, no. Just make sure you remember it's coming in here. Path will travel like this. So this is the entrance path. It bends down. So that means if I use the right hand, I want my thumb to point up. So if I put my finger along the x-axis for my thumb to point up, my fingers have to point into the page. So that means the field in this region is what? I shouldn't be answering the question for you. And why does it bend the opposite way? Well, when it's coming back in the opposite direction, right? When it's coming in this direction and it enters the field, if I put my finger, my index finger, along the direction it's moving, and I put my fingers along the direction of the field, my middle fingers into the screen, my thumb points down. So if my thumb points down, what does an electron do? It bends up. And whatever bending happens this way happens this way. Why? Because the velocity doesn't change. And since the curvature of this doesn't change, right, you can see if the field were stronger, the radius of the circle would change, right? Because remember now, go back to that equation that we were using. QVB equals mv squared over r. That's what I remember, because I know that's the force, and one of the v's cancel. And so if we're looking for the field is going to be equal to the mass times the velocity divided by the charge. And so we know it's an electron, so we know its mass. We know it's electron, we know its charge. We can measure the velocity because the information is there to measure it. It doesn't give us the velocity, but you'll have to collect the data and measure it. This is a lab. And you can get the radius of the circle. How? You're going to have to measure it. Okay, so I think that's enough on this one. Let's move to the next one. Okay, next one. Let's see if it'll play for me. So we see we have, what, 6 different particles coming in. So this is the same thing. Charged particles entering a magnetic field. The same equation we used last time. What do we know? The field has to be the same. There's just one field. So what's different about the particles? Well, either their charge or their velocity. And once again, you can measure the velocities. You can measure the radius of the circle. And with the information given, you can calculate the magnetic field. So we're going to jump ahead to number 9, the velocity selector, because that's part of number 8. So here are our 2 magnets. So there's a magnetic field going this way, kind of into the page. And then we have 2 plates. So electric field goes from positive to negative. There's a field down. So if a charged particle enters here, positive particle, right? The electric field is down. The electric force on that particle is going to be down. And the electric force is QE. And yet, if we do our right-hand rule number 1, we go along the x-axis, the magnetic field is into the page, so the magnetic force is up. That wants to bend it up. The electric field wants to bend it down. The magnetic force is QVB, because the sine of theta is 1. And so the magnetic force and the electric force may or may not be equal. So since once we set the plate voltage and the distance, we have a magnetic field and the charge. So this force is fixed. But this force depends not only on the magnetic field and the charge, but the velocity. So if particles go in with different velocities, the slower one is going to have a weaker force and it's going to bend down. The one that comes in fast will have a bigger magnetic force and it'll bend up. And there'll be just one velocity at which the particle goes straight through. That's why it's called a velocity selector. So by changing either the magnetic field or the electric field, we will select a different velocity. And so how does that work? In order for the particle to go through, QVB should be equal to QE. So since the charge is the same in both cases, the velocity of the particle that goes straight through will be the velocity that's equal to E over B. That's the selected velocity. And so that's how that works. And this is just another diagram that shows it. Now the field is coming out, the electric field is up, so things are reversed, but they're both reversed, so the direction of deflection is the same, and the particle that goes through, once again, is the particle which has its velocity equal to the ratio of E to B. Okay, that will allow you to do number 9. I did download this picture, so I'm going to show you this one. So in this case, here's cathode is the negative plate. You can tell from the battery. Notice the battery voltage. This is a negative plate. This is a positive plate. And so if we put a high enough voltage across here and we pull electrons off of the negative plate, they're going to accelerate across, and those that happen to pass through the hole in the positive plate, this is a device we have in lab that again you don't get to see, they're going to travel through and they come to an area, right, where there's a magnetic field going this way and an electric field going down, and so that's our velocity selector situation, and some of them bend up and some of them go straight through and some of them go straight, and we can detect actually where they end up if we put a fluorescent screen here where the electrons hit. It'll cause a point of light on the screen. So this is something to give you a more realistic sense of some of these very abstract diagrams that you're seeing. So I think I've told you enough to be able to solve this one. So you see you can control the field, you can turn it on and off. If there's no field, it goes straight through, and then if we launch the thing and turn the field on, whoops, I guess we got to turn it on before I launch it. Now the field is on, so it bends that way. So you can tell the charge on the particle, right, because you know the direction of the field. And then if we turn the magnetic field off and the electric field on, and we run it again, it bends the other way. Okay, so you can play around with this, and you should play around with it. It's a lab. And then answer the questions. I think you know the physics you need to answer all the questions. So going back to number 8, we have two parts here. We have the velocity selector, and then we have this area of just field. So what's going to happen is, let's see what happens. Oops. Reset. Start. The particle goes through, so it has the right velocity. We can get the velocity, and then it moves in a circle. So it goes in and comes out, and we can measure the radius of the circle. And so using that same QVB equals mv squared over r, that's the equation we use for the velocity selector. That's the equation we use here. And when we're in here, the particle here is subject to two opposite forces. Now it's just subject to a single force, remember, which remains perpendicular, so the velocity doesn't change, and it causes it to move in a circle. And since we can measure everything, the velocity, the radius of the circle, the Oh, you're asked to get Q over M, so you're going to get the Q over M ratio of this particle. So we don't know Q, so we can only get Q over M. If we knew Q, then we could get M. That's why it's called a mass spectrometer, or this is a type of mass spectrometer. And so if we did know Q, we could get M, and M would be the way we could identify the material, and that's how chemists use mass spectrometers to identify unknown materials. So here's another schematic diagram of the mass spectrometer. And you have an assignment problem like this too, where you see you have the electric plates and the magnetic field, perpendicular directions, and then it enters this uniform field, and it lands on a photographic plate in this case, where it leaves a spot. And so from that location you can measure. Remember, you're measuring the diameter of the circle here, and you need the radius in the equation, so don't make that mistake. And in real life, here's an industrial research grade mass spectrometer, so it's just this big thing. You can't really see much of the details, but they are used in chemistry labs, and we have some at HCC, although I think we have older ones. They are quite expensive, but here's a chemistry lab size style mass spectrometer, but when you see it, the electric plates and the magnetic field and everything else is all internal to the box that you see. But these are real devices that are used by chemists and others to identify materials. Okay, let's move on to the very last problem. So I think you can handle this one. This one's just back to the same old wire in a magnetic field. The current is along X, the field is along Z, the force is going to be along Y, right? F equals IL cross B, IL B sine theta. And since the force depends on the field and the current, and you can adjust the field, you can see the force changing. So if we put everything to 0, then the scale is just reading the weight of the wire. And we see the current actually causes the scale reading to go down, because now there's a magnetic force up, which means the only force isn't mg. The force is mg plus the electric force in the opposite direction. And by adjusting the field, the force gets bigger, and so you can play around with these things and adjust the force. And you should, again, it's a lab, play around with it and see if you understand why it's responding and how it's responding. This is right, and for this you would want, absolutely want, a free body diagram of the wire. So here's the wire, and what are the forces? The force is the scale holding it up, and that's the force that you see. And then there's the mg going down. I'm not drawing these to scale. And then there's going to be an a magnetic force going up. Now that force may be 0. If you turn everything off and the FB, the magnetic force, is 0, then the scale force and the weight of the object are going to be equal and opposite, right? Because the sum of the forces have to be 0. In no case does the thing move. But as we make this force bigger, mg stays the same, the scale force gets less. So this is just good old-fashioned first semester physics 111, Newton's second law physics. So you should be good.